let's go. So, in order to start, we need to open some windows. So the example of R5 is one window, and I think it's better if I use a different window. And then I think also the wave forcing, we open it in another window. And that's it. Okay. So, sorry. Let's start line by line from the example of our file. And while we move forward, I will explain to you everything is needed, including the structure of the wave forcing file. Okay, because some of you asked me what are the columns. Now let's move forward one by one. And just 1 second, I need also the PDF. Now we are everything. Okay. Let's move forward from the beginning. First of all, when you see what is the name in English of this chart here? Hashtag. It's a comment now. Okay. So basically, this after the hashtag, nothing is read. Okay. Okay. Let's start by copying these first lines from the example R file with right copy, and then go to the console, R console. Before pasting, let me remove the previous variable in order not to, I think it was A, B, and C. You see that I removed multiple entries at a time. Okay, now there is nothing here, I can paste. Okay, good. You see that in pasting, I gave an input, I defined some variables. The first variable that I define is RHOS, which is the sediment mass density. The sediment mass density, this is a typical value, 2650 kilograms per cubic meter. And then I gave as input, I defined the seawater mass density, 1025 kilograms per cubic meter. The gravity acceleration, the porosity of the sediments. Here there is a mistake. I wrote porosity is 0.6, instead it's 0.4. I need to correct the file, I will change it. And then K, do you remember K is the parameter, the empirical parameter of the CPLC formula, 0.7. Keep in mind that R makes a difference between lowercase and uppercase, so K with lowercase wouldn't be found. Time conversion is not needed.
K should be uppercase?
Yeah. Time conversion is not needed. Okay. Let's go back here. T equals 0, I'm defining the time index. And now you see a scan. A scan of cost.txt. So basically, I define a variable, I cut and paste. PR1, let me see. Okay, there is no cost.txt. It is correct because I need to give the path. Okay, good. And this is, remember these are the x coordinates of the current shoreline and the limiting shoreline, x. Now I need to introduce the y's. order to introduce the y's, first of all, I define. Okay. This is an important thing. I need to make a comment on this instruction here. Because let's look at cost.txt, the file, cost.txt. I go to my desktop. Unfortunately, here it is. You see that it's a file with 20 lines and 2 columns. What I am expecting after scanning it in R is that I find in a vector, line by line, these numbers. So I expect that the first number in the vector is 426, the second number in the vector is 380, the third number is 429, etc. Let me check if it is like that. PR1. Correct. But I cannot use this vector because it's a mix of the 2 columns. I need to separate the 2 columns. A way for doing that in R is creating a matrix by taking the numbers into the vector, into the matrix, and specifying that the matrix has 2 columns and 20 rows. So PR1 equal to array, the matrix, of PR1 itself. The dimension is a vector 2, 20. Good. This is the instruction. Look at the arguments of the function array. The first argument is the vector with the data. The second argument is the dimension of the array that I want to create. I hope it is the same instruction as in the file. Let me see. Yeah. Now, if I did it correctly, if I type PR1, 1, comma, what does this instruction do? It should display the first column of the matrix. Let's see. This is correct. If I look at the file, cost.txt, you see that indeed I got the first column of the matrix. Let me see if I can. You see? Perfect. 426, 429, 431, 450. Good. And this is the geometry of the current coastline. If I display PR2, comma, this is the geometry of the limiting coastline. And this is x, the x coordinate. So, please note what I did in transforming the vector into a matrix. This is the way you should upload matrices in R. First, you scan the matrix by obtaining a vector, and then you transform the vector back into a matrix. And keep in mind that it is a bit tricky to specify the dimension, because you may be in doubt whether the correct dimension is 2, 20 rather than 20, 2. So you have to check that the result that you obtain is fine. And the way you can check it, it's as I did. Basically, I took the matrix and checked the original matrix in the text file and checked that what I have in R corresponds to that. And I want to be clear. Let's suppose that we made a mistake. Let me rescan PR1. And let's suppose that we make a mistake. We make a wrong specification of the dimension because I inverted lines with columns, and And you don't realize it. The only way to realize it is to do like this, to check. I try to visualize, oh sorry, I made a mistake. Yeah. I visualize what I think is the first column, and I check that it's not the first column, it's a mix, first, second. So I made a mistake here. So be careful, because I tell you to be careful, because I made this error several times. It's not so easy to remember what is the correct way of giving the dimension of a matrix. Okay, now let's go back with the correct dimension. And then we are fine. Good. But this is just the X. Now I have to upload the Y. Yeah.
Why don't you change the directory of R? This way, not each time we have to put C users Alberto.
Yeah, correct.
I mean, it's easy, just file directory.
Yes. How did you set it?
Just file. I click on file.
On file. Ah, okay, that's perfect.
And change directory.
Okay, and how did you do in Linux? In Ubuntu?
No, I'm using Windows.
Ah, okay, perfect. Okay, thank you for the suggestion. Okay, good. Okay, perfect. Let's move forward with the definition of the Y's now. And let me get the example of our file. And in order to get the Y's, we have to scan wave forcing. And let me copy this instruction in R and let's comment on it. I'm just saying that it has to scan wave forcing for one number. Let's look at wave forcing now. Just here it is. You see that wave forcing, the first number is 150, which is the day Y. In the text of the exercise, if you look at the text, which is somewhere here, the coordinates along the y-axis are equally spaced with a step of 150 meters. Okay, and in fact, the step is reported here in the wave forcing. We have to upload it. Of course, we could also write the y equal to 150, but I just wanted to make the exercise of, and it should work because I already set the directory in my desktop. Perfect. And if I see the y, no, it's capital, no, not good. 150, good. Okay. So this is my dy. In order to construct the column of the y's, I need to integrate the y. And so I am expecting an instruction. Let me check for it. Okay, let's scan the t, which is again in the wave forcing. And look, here I am skipping one number, and the reason why I'm skipping one number is that the first number is already uploaded. Okay, the t, 120 seconds. Good. Let's go back here. Now we have to scan the number of the step of the simulation. Okay. Which is 1000. Good. Now let's build, I want to display the geometry of the coastline in a plot. So let's build the y, so let's skip some instructions now, and let's keep the series of the y. And let me make clear what I am doing before pasting. want to build a plot and for, with showing the coastline, and I already uploaded the x coordinates of the coastline. So along the x-axis, I already have the numbers uploaded. I need to build the y, and I know the y's, and I know that the dimension of x is 20 numbers, 20 coordinates. So for x I have 20 coordinates. Therefore I have to build a vector of y's with 20 numbers, equally spaced of the y starting from 0 conventionally. And therefore what I need to do is, given that I have a series of the y, I need to make y1 is equal to 0. y2 is equal to 0 plus the y. y3 equal to 0 plus 3 the y, etc. Sorry if it's trivial, but I want it to be fully understood. Okay, how to do this in R? Basically, what we have to do, as you see from this sequence, is to build a sequence of the y, 20 of them, and then integrate them. And this is the instruction. Cum sum is cumulated sum of what? It's a function, so round parentheses, repetition, rep is a function that repeats a given number n times. Repetition of the y, comma, 20 times. Okay, and if I now type y, this is what we wanted to obtain. Perfect. Now we have the y's, and we can write a plot. But look, the plot is a bit particular because we have two x. One is the geometry of the current shoreline, and the second one, the second series of x, is the limiting geometry. We have to display both of them. Okay, so the instruction is plot again, and the plot allows us to plot not only vectors, but also dispersion plots, xy. But first we have to give the x, and let me see, because I don't remember how I called it. I need to check. It's XLC1, oh, okay, XLC, XLC1, okay, XLC, Y. Let's make this attempt, and why not? Probably because I forgot to...
You didn't copy this.
I didn't copy this, yeah. So basically I created the array PR2, but in order to simplify your understanding, let's define two vectors, one with the first column of the array and the second one with the second column of the array. Okay, so let me do this. No, sorry. Copy and paste. Now I can make my plot. Here is the plot. This is a very simple plot with dots. But you see that you can see the shape of a shoreline. And let's make a plot with a line. Okay, perfect. In this way it's more visible. Good. And what about the limiting geometry? The limiting geometry needs to be superimposed over this plot. And then what we can do is use a function called lines. Lines writes a line over an existing plot. Here it is. Yeah.
I cannot plot the top one.
It's not one, it's L. You need to write L. You know, one is very similar to L. Now, let's recreate this plot in a finer way. Let me look at what is written on the website. Here it is. Oh, it's more or less similar. The only thing is that there is a different column, a color for the second line. You see, look at the further argument, col equal red, which allows you to plot lines in a different color. Okay, now, this is just our starting point. Again, the black line is the show line, the red line is limit. We will not use that limit here, because the software, the code is not conceived, not yet. You may try to modify it. Not yet conceived for fixing a limit, but still there are the premises. Okay. What do we need to do now? Now we have to look at the wave forcing and apply the CERC formula. The wave forcing is here. What are these 5 columns? Let's see what they are. I remind you that there is a redundant information here. We don't need everything. So let's see what they are. Let's look at the PDF. Okay. 4 or 5 columns. They are 5. Okay. Here there is an imprecision. This should be 5. Okay. I need to change it. Position of wave breaker line. And it means in terms of distance from the corresponding x. What does it mean? Look at the plot. It means that x is here along the abscissa. The breaker line, you see the first column is here, 37 meters, 44 meters, 52 meters. What does it mean? It means that with respect to the x of this black line, if you add the first column, you get the position of the breaker line. We don't need it, but just to clarify what it is, it's the position of the breaker. The breaker line, you understand what it means. It means what the typical line or wave break. Okay, let's look at the second column. The wave height of the breaker line, and this is needed. Okay. Third column, the wavelength at the breaker line. I don't think this is needed. 4, sea bottom depth at the breaker line is dB with respect to the mean sea level. And then there is one last column, the wave angle alpha with respect to the y-axis. Okay, let's spend a couple of minutes on this. So we have a coastline that is shaped more or less like this. And now we have an angle of approach of waves to each step, to each spatial step, we allow for the wave to change their direction for diffraction, for instance, while moving along the shoreline. So let's suppose that here in this spatial step here, the angle is this. Okay, so the velocity vector is this one. Good. So what is the wave angle? Let's read here. The wave angle with respect to the y-axis and between parentheses, the wave angle is equal to 180, so pi, when waves are directed along the y-axis and oriented towards increasing y. What does it mean? It means that alpha is this angle here. Because, look, if the wave was directed along y, along increasing y, you would get this angle alpha equal to 180, which is what is written there. It's extremely important when you read this to understand what's meant for wave angle, because you get a file with written wave angle, and it's 90 degrees. And angle with respect to what? It's extremely important that you read. If you download data from a website, there might be different conventions in the US with respect to Europe. You have to fully understand what it means wave angle. And in this way, I need it to be very clear. So this is the wave angle that I need. But you may find different conventions in other institutions. Okay, so this is alpha. And again, alpha is different, so when you move here, you may have a wave, you know that wave tends to approach the coastline perpendicularly. So what I'm expecting here is that the wave angle is slightly changed. Maybe that it's not perpendicular, but it's not the same. Okay, here it's more or less the same, but anyway, there is a change. You expect a change of the wave angle, and indeed, here it changes. You can keep it constant, no problem, but in general it should change. And the nice thing of applying a numerical integration is that for each delta x, you can change the data. Okay, so now we have a full perception of what these numbers mean. So the wave angle is in radians. Okay, keep in mind just that this wave angle is lower or equal than pi. It's lower than pi, but it's lower than pi, but it's higher than pi half, because pi half is 170, so it's between pi half and pi. Just to understand what kind of angle it is. It's like this one, okay? Because pi would be 180, pi half would be perpendicular here. It's between pi half and pi. Okay. And of course you don't expect a big change in the wave angle, because of obvious reasons. You don't expect, if you have a wave here in this way, you don't expect another way. Actually, in a real situation it may happen, but in this case it's not a big change. In the linear theory you don't expect really big change. Okay. At this stage, we need to upload this data. Sorry, this is my column. I uploaded up to here, up to 1000. Now I need to upload this matrix. So again, I need to guess the dimension, and it's 5 columns, 20 lines. Okay, let's upload it. And here you see how we do it. And it's here too. Yeah, it's here. Maybe that I already uploaded it, I'm not sure. No, I don't think so. Okay. 100 items, fine. 20 times 5. Be careful, every time that you can check that what you do is correct, you need to do it. So when you see an output like this, 100 items, just think of what you are doing and check if it is fine. Keep in mind that when you program, when you work with the BC, it's impossible not to make mistakes. If you create a new program, it's normal for a programmer to make mistakes. So verification is an essential step of programming. And verification can be done by systematically testing what you're doing. Good. Now I need to upload the dimension of the matrix. So PR2, let's create an array with dimension 520. Good. And then here you see that there is the assignment of each of the columns to a vector. Here it is. So DLF is position of the breaker line, HD is wave height, LF is wave length, dB is C bottom left, alpha is the wave angle. And you see that I'm trying to use the same symbols that I used in my lecture. And now we have everything we need to compute the CRC formula, to apply the CRC formula. Of course, this has to be done for each time step and each spatial step. So I need to apply the CRC at each time step, and we have 1,000 time steps. At each time step, I need to apply the formula at each spatial step. So first of all, I take a picture, time step, and then this is my picture, position of the shoreline, because it changes at each time step. The position of the shoreline changes because of accretion and erosion. Therefore, this is a picture at time 0. I need to apply the CRC to compute all the segment transport. I need to apply the one-line model. Do you remember? Shift the coastline back or forth. I show you a picture there. And then I pass to the next time step. One-line model. Let me go back and remind you what is. Here it is. Sorry. So, you see in this figure, this is a spatial step, a fixed time step. I have application of CERC at the previous spatial step. Let's suppose that it's below here, and the application of the CERC gives to me Q in. Q in is sediment rate, volumetric sediment rate in entering into my spatial step that I'm considering now. And then I apply the CRC to my spatial step, the one that you see there, and I estimate Q out, sediment out. There is a difference between sediment in and sediment out. It may be that in is greater than out, which means that there is deposition of sediment, accretion of the beach, and therefore I need to estimate the accretion, the yellow volume, and in particular I have to estimate the delta C up there, here, this one, delta C, and the way I estimate delta C is that I know the volume, the yellow volume, because I know the sediment volume rate entering Q in and the sediment volume out, Q out. And therefore the difference gives me the volume, the yellow volume. Okay? I know also the geometry of this volume because I am assuming one line model, which means that the shoreline moves back and forth by keeping the same geometry, and therefore, and the same slope of the beach, everything, and therefore it's easy to estimate delta Xi. It's tricky to understand whether delta Xi is negative or positive. Basically, it should take a sign such that when Q in is greater than Q out, I have a creation of the beach that goes into the sea. When Q in is lower than Q out, delta Xi should be such that the beach moves back into the land. And of course, the sign is something that we need to consider carefully. And keep in mind that if the wave angle changes, the movement, the direction of the sediment changes. So now I have a vector that is based like this. If the vector takes this direction, I have sediments that tend to move, or let's say the energy of the waves tend to move in this shoreline direction. If I have a wave approaching in this way, the flux of energy is in the opposite direction. And the flux of energy, by assumption of the CE formula, is proportional to the flux of sediments. So I have sediments that can move either in this direction or in the other direction, so I have to be careful of the signs